the break. Now we are starting the second session of our workshop. Now for the second session we are going to start the tutorial by Rahul Gopinath. He's a lecturer at the University of Sydney, Australia, and a great researcher on mutation testing. I cite him a lot, by the way. And today he's going to give us a tutorial on learning and refining input grammars for effective fuzzing. I shared with you the link to the tutorial. It's on the chat. And well, welcome, Rahul. I hope you have a wonderful time at the workshop, and the floor is yours.
Give me a second.
Okay, no problem. And
I don't have access to sharing this window. Let me see again. Okay, I need to enable something before I can share. Sorry about that.
I think.
Yeah, I think so. I did not have this problem in Zoom, so I was not aware of.
Are you using Google Chrome?
I'm using Opera, which is I couldn't use Google Chrome because it was giving me a repeated looping for redirection. Okay, so
no problem.
This.
And everyone, if you have questions during the tutorial, you can type them on the chat. And during the question and answer, you can also ask them yourselves. So, yeah.
Okay. I need to quit and reopen before the permissions are.
Okay, let's just wait a little bit more. Everyone, stay tuned. And just after the tutorial, we are going to have a quick break. No quick break. No quick break. After the tutorial, we're going to have a paper session. So stay tuned, everyone. Now we can see your screen, Rahul.
Okay, thank you. That is great news. Wonderful news. Okay, I hope you are able to see my window. Not yet. I can see. Not yet. Okay, so are you able to see the learning and refining input grammars for effective fuzzing? Hello, Giovanni. Are you able to? Okay. Okay, so again, thank you so much for introducing me. I am currently a lecturer at the University of Sydney, Australia. And my main research is on static and dynamic analysis of software, with a focus on fuzzing and specification mining. So before I start, please go to my SBST GitHub webpage, and you will need Python 3.10 to follow along in this project. Other versions of Python might work, but Python 3.10 is where I have tested this. And once you have Python 3.10, install the Jupyter notebook. Then clone the repository and finally start Jupyter within the repository directory. So I already assume that you have the Python and you have installed Jupyter. And here is how you would start the Jupyter notebook. Once you start the Jupyter notebook, you would be presented with a tree, a structure like this. This is the Jupyter notebook structure, and these contains our notebooks. So once we have that, the roadmap actually contains the organization of this tutorial. You can click on the roadmap. So here's the roadmap. So when you click on the roadmap opens up, and here are the links to each of these GitHub Jupyter notebooks, and you can follow along on each of the notebooks. For example, you should go to the prerequisites, and you should actually run it all. Click on the kernel, and then restart and run it all, so as to make sure that all the prerequisites are completely executed. So this contains a few of the Python packages, a few of the Jupyter notebook packages that are important, especially the side index that you see. That is a Jupyter extension that you will want. So once you have that, so let us now start our tutorial. Now, search-based software testing is the application of optimizing search techniques to solve problems in software testing. One of the chief concerns in software testing and search-based engineering in general is defining the search space, because in most cases, the effectiveness of our technique depends on the search space that you have defined. Now, if the search space is too large, then it may be impossible to explore it effectively within the budget that you have. So for search-based software testing, the search space is defined by the input space. And especially for fuzzing, it is defined by the input space. So in this tutorial, I'll be focusing on effective techniques to reduce the input space of the programs. In particular, since the theme of this year's SBST is fuzzing, I'll be focusing on how to make fuzzing more effective by constraining your input space. And in this tutorial, we will examine a suite of techniques that you can use on real-world programs to focus your searching techniques search space. Now, the example that I use is fairly simple, but it can be applied to pretty much most of the parsers in the world. And I have worked out examples that you can actually look at for other examples. So let us consider fuzzing. So fuzzing is fairly simple. The idea is that no system should crash when you are given any input. So fuzzers try to generate random inputs that can induce crashes when the system is under test. So here is how we fuzz. We generate random input, which is then fed into the program. If the program crashes, then we have found a likely vulnerability because the input was unexpected by the program. That is, there's a logical flaw that could be subverted. Now, fuzzing is effective if the fuzzer can generate sufficient inputs that can exercise all parts of the program. And naive fuzzing is not very useful when the program under fuzzing expects even moderately complex inputs. For example, we use feedback-driven fuzzers such as AFL, and these are typically paired with search algorithms to ensure that the fuzzers can penetrate deeper into the program. And we will see one such generator next, and that is in our tutorial. Okay. And second. So this is in generating samples. You should be able to see the generating input samples. And if you click it, then the Jupyter notebook will load. And within the generating samples, you can start execution. And I will explain the rest of the details along the way. So here we can import our calculator, which is essentially our guinea pig for the day. And we need an error handler. And then we have a simple random fuzzer. And this naive fuzzer simply generates a number of random characters, which are then we can actually feed that into the calculator. And let us see whether calculator actually, it generates anything that the calculator finds to be useful. So unfortunately, this is rather unsatisfying because generating it this way, a calculator is not going to actually find anything that is useful. I mean, these are totally random inputs, none of which is likely to get past the parser. So let us actually try observing the error. So if you add something extra, then calculator tells us precisely where this parse error occurred. Okay, this error occurred at character 5. So we can see that. And we can actually add this feedback to our fuzzer and make the fuzzer a little more intelligent. So you can say, okay, there is an unexpected character here. And if you add a non-terminated expression, then you can get a unterminated status. And you can also check whether a completed status is available, etc. Now, once we have this, then we can feed that to an evolutionary algorithm where we can simply say you have a fitness, a particular fitness if the input is complete. If you get an error that is unexpected, then the fitness is slightly different. And instead, if you have something unterminated, the fitness is again different. Now, in these places, you are actually the experts. This is a very naive evolutionary algorithm that I came up with just to show that this can be done. And we have an evolver, and we just verify that the evolver actually gets the fitnesses right. And once we have that, we create this initial population. Some error, but ignore that. And if you run all, you will actually find that it is able to generate fair inputs after a while. So these are generating inputs that can be that are actually accepted by the calculator sometimes. So here, this is accepted by the calculator. This is accepted by the calculator. So you can technically generate inputs that are accepted by the calculator. And we also have a similar example for JSON, where it tries to generate JSON inputs. Now, this is not all. Let's go back to the presentation. So for fuzzing parsers, we can make use of the search-based generation, as we said earlier. Now, another interesting technique that you can use is essentially to attach a feedback, attach instrumentation to it. And what we do is to adapt a hill climber. So we start with an empty string that is fed. So in the case of hill climber, our neighbors would essentially be anything that is one character extra to the program. So we start with an empty string and then try to generate its neighbors, which is one character extra long, and see whether the neighbors have a fitness that is beyond the previously existing string. So we start with an empty character, then attach a neighbor A, and then check whether it is actually accepted. But because we have instrumentation, we would know which characters this particular added character was compared with. Choose one of these characters, and then replace the neighbor with the next one. And then try again, attaching another character, and then choose again and again, until we reach a complete string. And we will see the implementation of this algorithm next. And this is in the track access notebook. Okay. So here again, for attaching the instrumentation, we use a proxy object. So the only instrumentation that we use here is essentially to proxy the input string. And we track the input characters, where exactly they are being accessed, in which location of the program these input characters are accessed, in the passed input string. Once the input string is transformed into any other data structure, we stop accessing. So this is the proxy object that we have. And then we can actually see that the proxy object is actually able to access to tell us exactly where these character access occurred. So here, because we looked for a space, we can see that. So here, the first proxy object is actually telling us about where the inputs came from. So if you actually split this my string into two, then the origins are actually mentioned specifically in the substrings that are produced. And again, if you create a range, then that particular range will also have a date. And then the xtxtr implements the comparison, the proxy object that captures the comparison. So here we do that. And then once we have that, then we look at our calculator, which is our example. So here's our calculator example. And then we'll see how we can actually modify the calculator example so that we can capture our input accesses. So we slightly rewrite the source code so that we can capture these input accesses. So we have a rewriter, and then that. And we can actually now capture all the character accesses in parse expression within the calculator. Now, once we have that, then we can simply run it through our fitness algorithm, a simple hill climber. And now you can see that the hill climber is actually able to generate values which are actually fairly reasonably calculatorish. So this is an example that will actually pass in to the calculator, and the calculator will accept it. And remember, we did this without the actual specification of the calculator. That is, we do not have the grammar of the calculator at this point. So if you can actually attach some amount of instrumentation, then you can manage to extract, to generate inputs for these input programs. So that is what we did. Now, this is actually very useful, but it's a little unsatisfying. The issue is this, that each time that you want to generate an input, we have to resolve our constraints again and again and again. And just for generating a single new input, you had to run through the entire solution, entire generation again. So this means that we are not actually making use of our testing budget that well. So this results in two major problems. The first is that it's very difficult to control the fuzzer without also impacting the non-deterministic behavior of the fuzzer. And this is important because we rely on the non-deterministic behavior of the fuzzer to be optimal in terms of search strategies. So we don't really want to impact on the non-deterministic behavior. And the second is that we spend our testing budget essentially essentially resolving the same constraints and again and again. So what is the solution here? One solution is to extract these constraints directly. That is, we want to constrain the search space. And how do we want to constrain the search space? We can actually extract the input grammar of the program that we are looking at. And once we have the input grammar, then we can use this input grammar to generate inputs that conform to this input grammar. And that will let us produce inputs that will get past the parser and into whatever is actually behind the parser. So this is what we will look at next. Now, what is a grammar? A grammar is a formal language description that specifies how an input is constructed. And there are different kinds of grammars based on the power of the grammar to construct increasingly complex inputs. And the simplest is the regular grammar, which can construct simple inputs that can be matched by state machines, that is regular expressions. And the next is a context-free grammar, next are context-free languages. And these require a stack attached to a state machine for recognition. And these are called push-down automata. And then we have things like recursively enumerable languages, which can be matched if you add one more stack to the push-down automata. And these are equivalent to Turing machines. Now, of these, context-free languages provide a good balance between the ease of parsing and generation and power. So most programs use context-free grammars as the base grammar. So we'll be focusing on context-free grammars in this tutorial. So here is an arithmetic expression grammar, which is a context-free grammar. And a context-free grammar is just like a procedure definition in programming languages. We have a number of keys that have associated definitions. And each definition contains multiple expansion rules, and each expansion rule defines one way to expand the non-terminal and contains terminal and non-terminal symbols. And each non-terminal symbol in turn has their own definitions. And terminal symbols are simply basic alphabets of the input. And the main grammars used in this tutorial are provided in this notebook. So if you go to the Jupyter notebook, you will see the grammar definitions here. And this contains our definition, and here is an example grammar. And that, as you can see, this is just a Python dictionary where the key represents the non-terminals and the definitions are simply a list of lists. And each internal list is the rule which contains a list of tokens. And a token can be a terminal symbol like plus or a non-terminal symbol like term. So this is an expression grammar, and this is a binary Boolean expression grammar. So these grammars can be used for parsing. For example, given the arithmetic grammar, we can parse the input 8 by 3 into 49 into a parse string. Again, we have a parser in our tutorial. These are all library functions that we use within the tutorial, but they are these are well-known external algorithms. So I will not be actually discussing what these algorithms are. This represents an early parser, which is a complete parser for context-free grammars. It can actually parse things like ambiguous grammars, and it can produce reasonable output in linear time if the grammar that is provided is non-ambiguous. And these are really good in terms of using the grammars that are produced and that are used by traditional programming languages. So this is a parser that you can actually look through. This is well documented. So let us go back to our tutorial again. Again, beyond the parsing, we can also use the grammars to generate nearly an infinite number of varied inputs, all conforming to the input specification. That is, given the input grammar, we can now go beyond the parser and reach deep code paths. And the grammars can also be very efficient in generating inputs. That is, we can now compile a grammar to produce a fast test input generator. And we have a test input generator, a grammar fuzzer, and that is the grammar fuzzer. And it produces fairly fast fuzzing. It produces fairly fast fuzzers. So we can use that in the tutorial. Now, grammar-based fuzzing is not a new idea. And there are a number of fuzzers that use grammars to generate inputs. The question is, where do we get these grammars from? And in many cases, the grammars may be available as a reference artifact. However, many programs do not come with a grammar. And even when they do, the provided input specification may not really be a whole story. So what do we do? The issue is that we cannot really trust the reference, the artifact, the grammar artifact that the developer may supply, if the developer actually decides to supply it. So what we can do is to mine the grammar from the program itself. And once we have this mined grammar, then we can use the mined grammar to generate inputs that get past the parser of the program. So going back, this is actually implemented in mining grammar. So that is 2.0 mining grammar. So it will take a little bit of time to show up. Okay. So, yeah. So before I start, let us go back to the keynote. And so the main idea here for mining the grammar is that the handwritten parsers that are actually used in these programs, they actually already encode the grammar in a recursive descent fashion. So if the program is written in recursive descent fashion, which is a traditional style, then that particular program already encodes the grammar in its control flow. So all that we have to do is to recover this grammar from the control flow. So what we do is to start by recovering the input string accesses. And we have already seen how to recover the string accesses from the control flow. So what we do here is to attach where in the program the input string characters were accessed. And once we have that, we attach the control flow information into that particular trace. And then we extract from that particular input comparison trace, we extract the dynamic control dependence trees that cover all features. And from the dynamic control dependence trees, we generate parse trees. So what is a control dependence graph? A control dependence graph is a graphical representation for the program where each statement gets a node. And there is a directed arrow between control dependent nodes. And statement B is control dependent on statement A if A determines if B executes. And each statement execution is represented as a separate node. And a dynamic control dependence tree is similar to a control dependence graph, except that we use statement executions. Essentially, each executed statement in a program is a node in the tree. And each statement execution is control dependent on the statement that caused it to execute. So in this tree, we attach the input indexes that we mined using the proxy string. And each input character is attached to a leaf node that accessed it last. And this makes the dynamic control dependence tree a parse tree. And here's an example parse tree for the arithmetic expression 9 plus 3 by 4. So let us see how that is done. So we come back here, and then we start. By importing all the inputs, and then we have a context-free a context manager that keeps track of where exactly in the program the character accesses are made. So I'm simply stepping through, but all these things are well documented. So once we have the context managers, we rewrite our program so as to use these context managers that attach the information on the control flow that is traversed by the program when it executes. So here is the context manager that contains a method and a while loop. And here is the stack wrapper. That's again another context manager. And we add. So here is our full program after rewriting. So here is our full program that includes the context managers that I talked about. See, so these are the context managers. So we wrap all the conditionals and the loop conditions in context managers. And this attaches the information as to the character accesses. Once we have that, and once we have this, then we are ready to generate a trace. So we execute this, and here is our trace. So these are the character accesses that were made when we executed the program with the input 9 minus 16 plus 6, 72 into 3 divided by 458. So you can see that the first character was accessed. The first access was made at 9. The first index was 9, and then it was accessed step by step by the parser. Now, once we have this, then we want to attach the information. We want to extract the information from this and then reconstruct our tree that I talked about. So here is how we extract it. Sorry. Graph is not executable, so that needs to be handled. Sorry about that. Export the path to the graph wizard variable, that is opt homebrew. Restart the Jupyter notebook. And we start mining grammars again. So it takes a little bit of time. Okay, so now we simply start the kernel and execute it fully for now. Okay, so first clear our inputs, and then we start it. So we were at mining the generated traces, and here. So we have our generated tree that actually extracted the complete parse tree from the program while it was running. And this is what I was talking about earlier. So now let us get back to working it. So now the next thing that we need to do, so we have the parse tree, but this parse tree is not fully abstract. These parse trees are actually specific to the particular execution that we just did. That is, we do not know which nodes are comparable, whether a particular digit node can be replaced with another digit node. And this is what we do in generalizing nodes. So we try to figure out which are the conditional nodes, which are the looping nodes, and whether the looping nodes actually require, which iterations of the loop are compatible with each other. Because sometimes one iteration may be compatible only with the odd numbered iterations, because there might be other things with Boolean variables that might be going on within the loop. So with one iteration of the loop may be looking for commas, and in another iteration it may be looking for digits. So we try to generalize the nodes. And how we do that? Essentially look at each of these nodes. So here, if you see, this is our parse expression, the derivation tree that we generated from 9 plus 3 by 4. If you look at the two while nodes, you see that in the first place, the first iteration of the while loop, the digit 9 was parsed, but in the next iteration of the while loop, an operator was parsed. So we cannot actually replace the first while node with the second while node. And this is why we need to actually generalize. And what we do is to compare each of the nodes that are named similarly. And then we try swapping them and check whether the resulting value is actually accepted by the program. If they are accepted, then they are compatible nodes. So we do the same thing with parse expressions. So we generate an expression by swapping one parse expression with the other, and then check whether it is compatible. And if it is, then we mark them as compatible nodes. And in here, we check whether the two while nodes are compatible. That is, we switch between the multiplication operator and the parenthesis. And that results in an input that is not compatible. So that means that these two while nodes are not compatible. So once we have that, we actually have a derivation tree where we actually can extract the grammar from. And this is what we will see in the next. So going back, so we now generalize the nodes. And then from there, we extract the grammar. And here is the grammar that we extracted. So this is not very nice to look at present. But what we do is that we can recursively improve, we can iteratively improve this grammar to generate more and more better grammars. And the nice thing is that once we have this grammar, then that grammar generates inputs that are completely acceptable by the program. Any number of inputs, and it will generate. It can generate an infinite number of inputs. So we are here. And the way that we actually generate the grammar is to actually start with the root node and then extract all the first level children of it. And the names of the children becomes the tokens in the rules. And we extract each similar rule and then add the rules. And from there, we abstract the final grammar by looking at which nodes are repeating and others. And here is recovered arithmetic grammar. Actually, I have an example here. So let's see. Yeah, sure. Okay, so I just want to show an example grammar here. So here is the full example. Okay. So it will take a little bit of time. So let me go further into the keynote. And once we have this grammar, we can generate any number of inputs. And another entire set of extracted grammars are available in my GitHub page. And this contains grammars extracted from JavaScript, from JSON, from C, and any number of programming languages, and CJD code and others. Now, what happens if you find a crash? So before that, let me actually go back here. Somehow my Jupyter notebook is fairly slow today. So I'm going to close off these things. Okay. Since I don't have a lot of time, so let's see what happens if you find a crash. So why did the program crash? And we can use the delta debugging to minimize the failure-inducing input. Okay, but however, this new input is really tiny, but it doesn't actually tell you why the crash happened. For example, would any of these things crash? That is it 5 characters that caused it a crash? Or is it the double parenthesis or the presence of 5? So what exactly is the cause of the crash? So can we do better? And this is what I tackle in abstracting inputs. And in abstracting inputs, so again, so these are a few bugs from real world projects. And each of these are minimized test cases. While they look simple, they aren't actually telling us anything more about what caused the crash. So for example, are the repeating variables important? Are empty objects important? What if you have other declarations? So the question is how exactly we can do that? And the solution that we found is to parse the failure-inducing input and then try to generalize it by repeatedly replacing each node with a set of nodes that are automatically generated. And if all the nodes that are generated that way is accepted by the program and reproduces the hash, then we know that we can actually abstract that input. And that produces an abstract failure-inducing input. And this gives us a specialized grammar. Actually, this is provided. Okay, so before we go there, so that is provided in the abstracting inputs page. And you can see that I actually tried to abstract a failure-inducing input. And I am actually able to produce input. So what I'm trying to abstract is a simple value. If the input contains double parentheses, then fail. And you can see that I am able to. So this is a failure-inducing input. 1 plus double parentheses 2 into 3 by 4. And we can abstract that and finally obtain a grammar that only generates inputs that contain double parentheses. Now, this is interesting, but can we do better? And this is what we do in the final notebook, that is input algebras. So in input algebras, what we do, so in input algebras, what we actually do is to try and combine different failure-causing inputs. So with abstract inputs, we have a grammar that specifically focuses on a particular pattern. It generalizes a particular pattern, and it will only produce inputs that matches a particular pattern. It may be like double parenthesis, or it may be division by 0, or any number of such patterns. And what input algebras does is to actually combine them together. You can say that a particular input contains both division by 0 as well as double parentheses. Or you could also say that this particular input contains double parentheses but does not contain numbers 5 to 9 or any number of such features. So what we have, so here is an example with JSON. So the first one is where we say that our program fails if the key value is null. And then we also want to negate that. And then we add one more condition. One key must be empty. And then we capture these both behaviors, and then we generate a grammar. And these are done automatically. Once we have that, we can generate a grammar that exactly produces whatever we actually wanted. So here I am simply saying that it should contain at least one item where there is an empty key, and it should not contain any null key values. And we can actually pass it to the tools that I produce and generate a grammar which would always generate inputs, and all inputs that actually allow this particular constraint. Okay. This is the final input algebras slide. And run that and see the results. Now, this is the grammar that actually that gets produced, and this is a constrained grammar that produces only inputs that correspond to the particular expression that you started with. So here the expression was it should contain both D1 and Z1. It should not contain either D1 or Z1. So at the end of this particular talk, I have talked about how we can generate valid inputs for programs without specification, and I have talked about how we can mine input grammars, and I have also shown abstracting the inputs so that you can generate any number of such inputs, and I have also shown how to combine such inputs using an algebra. So that ends my talk, and I am available for any questions.
Thank you very much, Rahul. Great tutorial. Very thorough explanation of how to implement everything, since even the evolutionary algorithm at the beginning. Very interesting. Thank you very much. And we still have a few minutes for questions, so if you all have questions, please put them in the chat or join in and ask them directly. I have a question meanwhile. When I was working with Fuzzing in the past, one of the few things that I read about on the literature review is the difficulty in getting past the parser, right? Getting valid inputs. I see that your solution of getting the grammars and then generating those valid inputs make you go past that parsing part. Is that that's obviously an advantage, but is that the only advantage of your solution, or what can you say about these difficulties in fuzzing and how grammars can solve them?
So thank you for the great question. So as you said, getting past the parser is the first step. Once you get past the parser, then you reach the system behavior. Okay. Until you reach the parser, you do not actually reach the system behavior. But once you have gotten past the parser, then you have interesting behaviors that you can actually examine. So for example, for understanding when a division by zero occurs in a calculator expression, you need to actually produce expressions that contain that division by zero. And that requires the extraction of the grammar. But once we have that, then we have the grammar, so we can minimize the input and precisely understand what caused this behavior. So it may be that there is a division by zero, or it may be that there is a floating point exception, or it may be that you have a null value somewhere. And in the third part of my tutorial, in the abstracting inputs, this is what I tackle. So this is what goes beyond just the parser. And once you have, essentially gotten this together, so if you have something that contains multiple faults, how you can actually decompose that and then combine them back together. You can say that you want to produce an input that does not contain a division by zero or does not contain nested parameters, but contains other bugs that you are interested in. So these are the things that I talked about in the last part. Unfortunately, it was a little more rushed, so it is not as detailed as I wanted it to.
Yeah, no worries. It was a great tutorial, by the way. Thank you for answering the question. I believe you have a question, Sebastiano?
Yeah. I mean, I'm very big fan of, fuzzy, because it can be applied in large scale. If you're going to talk to Google and then you mention about fuzzy, that's probably what they're applying. And I was talking with an engineering about that. I was more on a technical side. So what is the challenges or apply fuzzy in different languages? Did you see, moving from object-oriented to, Python, like it's more sort of scripting language, if you want, difficult, different, what would be the challenge, what are the available solution, or how transferable is your solution? What is your general thought about that when moving from programming languages?
So there is one clarification that I should make here. The techniques that I presented here, and these are all in Python notebooks, and even though I was not able to present it fully, you can still go through them. They are all language agnostic. They can be applied on pretty much any programming language that follows at least structural programming techniques. If the program does not follow structural programming techniques, what you will get is a more degraded version of the grammar, or at whichever portion of the program structural programming techniques like while loops, conditionals, etc. are in there, you might get a little more degraded grammar. But otherwise, what I have found is that we looked at Java, we looked at Python, we looked at C. And in all of these languages, we can apply these techniques. And there is, it is actually language agnostic. Super. And I have also mentioned that in my GitHub repository. This can be applied so long as you are able to actually, at least wrap the input string in a proxy so that you can find where in the program these input accesses occur. And this can be done in pretty much any programming language that is currently out there.
Yeah, I did ask intentionally because I think that's value of what you are proposing. And when I also, there would be some discussion about, and you have seen previously in Paolo keynotes, how to use systematic testing for AI and stability system. So if you move from actually programming languages, and you try to move forward to an AI and stability system, what do you think would be the challenging to move there, or there would be any? I know that is a bit teasing, but I like to link talks to previous people.
Yes, that's a really great question. How would any of these techniques have an application in AI or testing AI? One thing that it might have is at least in generating inputs. For generating inputs, we can actually generate inputs by considering the system as a black box, so long as the system obeys a very minimal, interface. That is, it should tell us when the input is incomplete, or it should tell us when the input. So if you provide a string to the system, it should either tell us that the input was valid, that is, the system can accept the input, or it should tell us it is a valid prefix, that if you attach something more, then it would become a complete string. Or it should say there is no way that the string is a valid prefix. If a system obeys these three constraints, then you can actually use the hill climber to generate inputs. And it doesn't really matter whether it is an AI sitting in the black box. Now, mining grammar is harder. Until now, I haven't seen a good way to mine grammar. However, there are efforts from Caroline Lemieux and others for mining grammars from black box systems. However, I'm not very sure how scalable these are. For once you have source code, of course, things completely change. But black box mining is still an ongoing research. But abstraction of inputs, certainly you can do that.
Would be one way to go.
Yeah, and combining these inputs, these can also be done. Thank you for
the question. Thanks, Rahul.
Thank you, Rahul. Thank you for your wonderful tutorial. Everyone, please congratulate on this amazing tutorial. And I guess now, if you have questions, please put them in the chat. And I think we can go to the